so in this equation we will be doing a von Neumann stability analysis of the finite difference equation that we derived in the last video. We also showed the graphing of the equation, and with the initial position being at 350 Kelvin, position capital J at 400 Kelvin, and the initial temperature being at 300 Kelvin, and we saw this graph of how the heat is diffused throughout the linear bar. We also saw that when we were changing the R value that we had these oscillations occur, and these are pretty extreme, but obviously that's not necessarily indicative of how the heat would diffuse across a linear bar. Using common sense, this doesn't make sense for the heat at one position to be here and then up and then down and then up. So we need the von Neumann stability analysis to see when is our equation stable, because as we go further and further to infinity, the equation will just become more and more unstable because of the repeated use. So using our equation, we can use a Fourier series to kind of look at our equation a little bit differently and further simplify. So we know that temperature is based off the position and the time, so we will make a sum using a constant for amplitude, e to the negative I k delta x, and then e to the heat diffusivity constant, k delta x, from k negative infinity to k infinity. We will use this series to further simplify this equation. So t of j plus 1 to the n is equal to t of j to the n, e to the I k delta x. So the series splits this j plus 1 kind of into two terms, the j to the n and then the e to the I k delta x, and this is positive because it's the next positive block forward on the linear bar. We'll do the same thing with the t to the j minus 1 of n, but it will be negative because it's one negative block backwards on the linear bar. So we'll plug these into our finite differencing equation. And then from here, we're going to use some algebra to further simplify. We're going to pull out the tjn term. That's an r. Also, using Euler's equation, we can simplify down to this cosine right here. So we have t, and we can further pull out the tjn. So tjn times 1 plus r 2 cosine, because this is divided by 2. And minus 2. And then we know that the absolute value of 1 plus r 2 cosine kx minus 2 must be less than 1. And we will further do algebra again to simplify further. So r 2 cosine of kx minus 2 then 0 and negative 2. And we can pull out the 2. That was dividing by a positive 2, so the qualities stay the same. And then we know that cosine has to be between negative 1 and 1. And if you plug in 1, it's equal to 0. So our equation will be valid. But if you plug in negative 1, you get negative 2. And we will divide by negative 2, which does flip the inequality sign. So then we have r 1/2 and 0. And we know that r has to be between 0 and 1/2, and that's why when we plugged in over 1/2 in the Python Google Colab code, it started these oscillations because it was becoming more and more unstable as we worked towards infinity. So I just wanted to point out that if you plug in negative 1 here, this term is 0, so it's negative 2. And if you plug in 1, it's positive 2, which makes this term 0. Just to further clarify that math.